Work. Work is an application of the integral, and it will calculate net change and total accumulation. All right, work is defined to be force times distance, where the force is constant. So let's take a look at this demonstration here. Work is equal to force times distance, and the force is the weight going from the bottom to the top, so this is going to be 1,000. The force does not change at all, it's always going to be 1,000 pounds, and you're going to times it by the distance, which is 2, and this is in pounds, this is in feet, so this answer will be 2,000 what we call foot pounds. It's a product. Okay, over here, the gentleman here is trying to push a wall. We don't have an indication how much force he's trying to exert, but the force is going to be, let's call it F. But what we know is he's not going to be able to change the distance, which is 0. So the work he does is 0. Over here, work is equal to force times distance. Unfortunately, this is a mass, and a mass is not a force. Over here, pounds is a force, and it has already the acceleration due to gravity incorporated within it, but this mass does not. So we need to take a look at how we deal with work in terms of the metric system. So a newton is what we call a force, and it has the mass portion of it, and it also has the acceleration due to gravity portion of it. So 1 newton is equal to 1 kilogram times meters per second squared. So when we take a newton, which is the force, and times it by the distance, so this is the force, and times the distance, that's going to be work, and that work is noted as a joule. Hooke's law for spring says that the force it takes to stretch or compress a spring, x units from its natural unstressed length, is a constant times x. So in symbols, this is it, force is equal to k times x. So k is what we call the spring constant. Look at all these springs. Some are harder to stretch or compress. Some are easier to stretch and compress. So that K is the characteristic of the spring. All right, now how are we going to use Hooke's law to determine how much work it takes to stretch a spring? So we have a force, it takes a force of 10 newtons to stretch a spring 2 meters beyond its natural length. How much work is done in stretching the spring 4 meters from its natural length? All right, so this information in the circle is going to help us find the spring constant. Remember, force is equal to K times X. And we know that 10 newtons, it takes 10 newtons right here, 10 newtons to stretch it 2 meters. And so that tells us that our constant is going to be 5 newtons per meter. So we can look at the force as 5x. And so the farther x goes, the more force it's going to take. The smaller x is, the less force it's going to take. So this is a force that is varying. All right, we want to decide how to set up our work. Remember, work is equal to force times distance. And in this case, our force varies. So it's not always constant. So how are we going to deal with this? Let's take a look at this. Is how much work we're going to apply to go from the natural length to this stretch length. And we're going to divide this into a number of intervals. And I'm going to take this interval right here. And the smaller the interval, the more the force seems constant. So a little piece of work here will be a little force, which is 5x sub 1, and then times the distance, delta x. And that'll be my x sub I, or I could say x sub 1. and that'll be x sub 1. Another piece of work here, so from here to here will be 5, and again how far it goes out, so this is x sub 2 times the little distance delta x, and again 5x sub 1 is going to represent a almost constant force because it's such a small interval that it doesn't vary too much. So in the end, we can represent our little piece of work as the force, which we're going to say 5x, times a little distance that it's taking. So that's what this is representing. Here's our force, here's our distance. And these distances amount from stretching to 4 meters. So it's going to go from 0 to 4. We're going to take the antiderivative, and then we're going to get the answer 40. And remember, this is in the metric system, so it's going to be newtons times meters. All right, find the work by this force, and you can see this force is varying depending on the x. The force changes along the x-axis from x equal to 0 to x equals half a meter. So I'm going to represent a little piece of work, which is force times a little distance, so delta x, and our force in this case is cosine of pi x delta x. And I want to sum up all of these works, so work will be equal to the integral from 0 to 1/2 cosine of pi x dx. And then this is going to be, the antiderivative will be sine of pi x divided by pi, evaluated from 0 to 1/2. And then this is going to be sine of pi halves over pi minus sine of 0 over pi. So this will be 1 over pi. And this is in newtons times Newton meters. And that's the work. And that work is going to be called joule. So I can say 1 over pi joules.